So hello everyone. Sorry for the extra lecture that wasn't planned, but just due to the pace of this course and the fact that I want you to be able to complete the homework and have plenty of time to work with the material that's present in the homework, we really should be moving on to chapter 15. So I'm creating this extra video to finish out chapter 14, which is focusing on entropy. And that way, we can spend a good amount of time covering it and maybe do some practice problems as well, just to get you to the point that you can approach the homework, feel confident on the quiz, and eventually, ace the final is the hope. So we've already seen these first few slides on how entropy is this quantitative, entity that encodes this idea of irreversibility. So we know that microscopic processes, you could have two particles collide and go off in different directions, but the reverse is just as easily imaginable. But there are some processes, like the development of an organism, that aren't easily reversible. Or, stirring chocolate syrup and milk together. It's easy to make chocolate milk, but it's quite difficult to make regular milk and chocolate syrup out of that. And so understanding irreversibility is really deeply tied to the field of entropy, which is a part of statistical mechanics. And so just to summarize what we talked about in the last lecture, we have the second law of thermodynamics, which tells us empirically that entropy in an isolated system can only ever increase or stay constant, and that it only stays constant when it's at its biggest possible value, which happens when a system is in equilibrium. So once we've mixed the chocolate milk up, the chocolate and the milk are, in some suspension, and in that process, they come into equilibrium. They're not separating, they're just thoroughly mixed. And so in that equilibrium state, the individual particles might still be moving around, bumping into each other, but the entropy of the system isn't changing. And one of the ways that we mentioned quantifying this was by thinking about the number of microstates of the system, which is a bit of an abstract idea that's encoded in this quantity omega here. So omega, which is the multiplicity, basically tells us for a statistical system how many states there are that the particles could occupy. And this can be a tricky idea to wrap your head around, but an example of one of these microstates is, for example, if I had a big list of the position, like the x, y, and z coordinates of each gas particle, and then their velocity vectors as well. So if I had a big list with all that information, like an Excel spreadsheet, that would be a microstate. But that's really hard to actually not only contemplate, but even store that much data for even a small amount of gas. Our best computers, our best data storage solutions can't handle it. And so we instead just imagine, to a very good approximation, that our system is occupying some microstate, and there are usually a whole bunch of microstates that would all give us the same macrostate. And by macrostate, what I mean there is these quantities like volume, pressure, temperature, all of the variables we've mentioned as we've gone through this thermodynamics unit are part of the macrostate of the system. And whenever we change some property of the macrostate, we might create more possible microstates, or we might reduce the number of possible microstates. And that basically is proportional to how we change the entropy. So for example, if we have gas, like in this image on the left here, so we have gas in this yellow region, and we allow the box to expand, it turns out if you go through the physics very carefully, you'll find that there are more ways for the particles to arrange themselves if they have a bigger box. And so when we allow the box to get bigger, we increase this omega, we increase the number of microstates, and we just assume that all of those microstates are equally probable for the system to be in. And when we do that, we get this entropy equation that S is kb ln omega. And the ln is the natural log, so logarithm base e. And so what that tells us is that as we increase omega, the entropy is going to get bigger and bigger, but not in a linear way. So if we double omega, we don't double the entropy. It actually grows more slowly. So it takes a large number of microstates for the entropy to start to increase. This is a good bit of intuition to have. And Boltzmann's constant, this kb here, which is something that we can look up when we need it. It's just some constant of nature. It'll be on your formula sheet. Is incredibly small because it's the ideal gas constant divided by Avogadro's number. Just to remind you, kb is the ideal gas constant over Avogadro's number. And Avogadro's number is something like 10 to the 23. So kb is incredibly tiny, which means that even in systems with tons and tons of microstates, we have a pretty small amount of entropy typically. And so, we could also think about the alternative. So going back to this box of gas, if we compress the box of gas, we decrease the volume, then in general, we'll make it such that there are fewer possible microstates that could give the observables that we actually see, the macro state. And so we decrease the entropy. And but remember from the second law of thermodynamics that for an isolated system, the entropy can never decrease. So if we're able to decrease the entropy, that means that somehow our system isn't isolated. It's not all a world of its own. It's having to give more entropy somewhere else. So if we decrease the entropy of something by 2 joules per Kelvin, then the entropy of something else has to increase by more than 2 joules per Kelvin, unless it's in equilibrium, in which case it would increase by exactly 2 joules per Kelvin. But in general, it'll increase by more, maybe 4 joules per Kelvin will go towards, the entropy of the air around an object, something like that. And so we'll get some practice with this. I know it's very confusing and abstract, but there's another important definition of entropy, and this is actually the older definition, which is that some small change in entropy is related to a small change in heat of a system over the temperature at that point in time. And so if we're working with systems that are at a constant temperature, then we can just say that S is Q over T. We can just easily integrate that if T is a constant. But if the temperature is changing, we have to be a bit more careful. We know that we're going to get some logarithm in there when we integrate, 1 over T dt, something along those lines. And so we'll see what those formulas look like, and the derivations for them are in the book, but they're all coming from this ds equals dq dt process. It's just we have to imagine how is Q related to T, if T is changing or if T is a constant. So just be cautious there. But before we get into using this more heat-based formula, we should get a little bit of practice with the multiplicity, the omega formula. So that's what this is allowing us to do. So we suggested earlier that the multiplicity of a real-world macro state is of the order 10 to the 10 to the 23. So this is an insanely large number. Whenever you take 10 to some power, it's going to be something big if it's a positive number. And if you do that again, you're going to get something unimaginably big. Okay. This number is way more than the number of protons in the entire universe, just to give you a sense of how big 10 to the 10 to the 23 is. And so just be cognizant of the fact that the number of microstates that are possible for a normal box of gas, like a room full of gas, like the one you're sitting in, it's just unimaginable, the number of microstates. So what is the entropy of such a system? Well, we can straightforwardly calculate this. So let me get my calculator here. So our entropy formula just says that the entropy of a system is KB ln omega. And so we can just plug in omega is the number of microstates. We just assume they're all equally likely for the system to be in, so we don't have to distinguish them. And so this is just KB ln 10 to the 10 to the 23. And then when you're taking the logarithm of something that's being raised to a power, one of our logarithm rules allows us to bring that power outside of the logarithm. So we have 10 to the 23 KB ln of 10. ln of 10 is just a number. You can type that into your calculator. And KB is a constant that we can look up. And when we plug these things in, we should get 3.2 joules per Kelvin. So you see, entropy has a weird unit. It's energy over temperature. And that's because entropy it's not like anything that we've learned about so far. It's its own distinct type of quantity. And so we shouldn't expect it to have units that match something that we've already learned about. It's telling us, a new thing about our system, which is kind of how chaotic is it, right? The more micro states that are possible, that means that we know less about the system. Because if there are more possible microstates, we're even less sure which one the system is in than we would be if there were fewer, although still typically a very large number. And so 3.2, though, is a very normal, healthy number, not anything unimaginable. And that's, like I said, because KB, Boltzmann's constant, is something like 8 over Avogadro's number. And so that's going to cancel nicely with the 10 to the 23 here. Okay, so then we should look more closely at how we can then interpret the entropy for these isolated systems. So like I said, the second law of thermodynamics says that for an isolated system, the entropy can only increase. So that's what this formula is saying here, that delta S isolated, this is how the entropy of an isolated system changes. It has to be a positive number. It has to increase, or it can be 0, but that only occurs in equilibrium. And we already saw this formula that ds is dq over t. And so if t is constant, we can just integrate both sides of this very easily. And then we arrive at this formula for isothermal systems, right? That's telling you that the t is constant, which is that the change in entropy. So now this isn't telling us S, this is telling us delta S due to some process is Q over T. And there aren't that many processes where the temperature stays the same. It's a tricky thing to do. You usually need some sort of big bath of water or something with a high heat capacity to surround your system. But there is an exception to that. There is a place where it's very easy to get a system to be isothermal, and that's when it's changing from one state of matter to another. So for example, when water goes from a solid ice to a liquid water, that whole process happens at 0 degrees Celsius. So that's an isothermal process. And so phase changes are going to use this simple entropy formula. It's just Q over T is delta S. And so let's see an example of that. This example asks, what is the entropy change of water when 100 grams of 0 degrees Celsius ice are slowly melted to 0 degrees Celsius liquid water? Okay, so our formula is just that delta S for this isothermal system is Q over T. And you might ask, what is the Q that we should use here? Well, it's the Q involved in melting this ice, which we learned the formula for is just M times LF, right? L fusion, latent heat of fusion. And so we can plug in 100 grams is 0.1 kilograms. We have to be careful to convert that. And the latent heat of fusion for water is 3.3 times 10 to the fifth joules per kilogram. So our units are going to cancel nicely, and we get 3.3 times 10 to the 4 joules of heat. And now all we have to do is divide by the temperature, and this is where we don't have a delta T, we just have a T, so we have to convert to Kelvin. So 0 degrees Celsius is a temperature of 273 Kelvin, and so if we divide 3.3 times 10 to the 4 by 273, we get our change in entropy of 122 joules per Kelvin, which is actually, quite a bit of entropy change. That's larger than the example we just saw a minute ago. And that tells us that when ice melts into water, the process that occurs where we, break down some of those intermolecular bonds and allow the water molecules to move more freely, that dramatically increases the number of possible microstates that the system could be in. So what that's saying is that there aren't that many ways that you can have ice, even though the molecules are more stuck in place with ice, they still have vibrations. And so there's still some degree of uncertainty about what the actual microscopic things are doing in your system. But once you turn that ice into liquid water, there's much more uncertainty about what the actual water molecules, what their velocity and positions are. And so we quantify that with entropy. You can really see how, instead of just having to say, oh, it's more chaotic, there's more possible stuff happening at the microscope, we can actually put a number to that, 122 joules per Kelvin. That's the number associated with ice going from a solid to a liquid. And all we needed to know for that calculation really was the temperature of the phase transition and the latent heat of fusion for the phase transition. So those two numbers characterize the change in entropy in the system. But notice that entropy does depend on how much stuff we have. If we have more stuff, we're going to have more possible microstates, so we're going to have more entropy. So there are lots of ways to write tricky questions where you might ask someone, which has more entropy, ice or liquid water? And you should pause a moment and say, well, how much ice? What mass of ice, and how much liquid water? What's the mass? Because even though in general liquid water is going to have a higher entropy, you have the same amount. If you had a ton of ice, like a glacier of ice, and versus a cup of water, the glacier of ice will have much more entropy. So be careful of that. Just because something is in an inherently more chaotic state, we can't ignore the fact that the mass is relevant for these calculations. Okay, so that's the problem on the left. Now on the right, for the same situation, so ice melting into water at 0 degrees Celsius, we now want to know, how does the multiplicity change? So how many more states, how many more microstates are there once you allow those bonds to break down and the water to become a liquid? And so let's calculate that. So I'll draw a little line here. So now we need to go back to our formula that S is KB ln omega. Oh, I guess I can't write off the edge, ln omega. But this tells us the actual entropy. And we want to know what is the change in entropy. So what we have to do is remember that the change in entropy is S final minus S initial. And so we're going to have KB ln omega final minus KB ln omega initial. But going back to our logarithmic properties that we learned, long ago in Algebra 2, if you're subtracting logarithms with the same base, that's just dividing their arguments. So we get KB ln of omega final over omega initial, and this is in the logarithm. Okay, and now we can just set these equal to each other. We got a number for delta S, and we have a formula for our KB ln omega F over omega I, a formula that involves the multiplicity. And the question just wants to know by what factor does the multiplicity increase. So that's just saying that it wants to know what is omega f over omega I. This is the thing that it's asking us to find. And so all we have to do is plug in KB and rearrange this equation. And so when we do that, we're going to have to take the sort of exponent of both sides. What I mean by that is we're going to have e to the 122 over KB equals e of ln of omega f over omega I. And the reason we do that is so that this side, e to the ln, cancels out. Those are the inverse functions of each other. And so we just get omega f over omega I. And so all we have to do now is actually plug in, so into your calculator, e to the 122 over kb. And I don't know if we've said it recently, but let me write it up here. So kb is 1.4 times 10 to the negative 23 joules per Kelvin. And so plugging that in, we get an omega f over omega I. Which we can write in scientific notation as 10 to the 3.8 times 10 to the 24. So this is an insanely large number. If you try to evaluate this with your calculator, you'll have some trouble because your calculator won't like dealing with such a big number. So what you may have to do is just calculate this exponent on its own, just do 122 over kb. Your calculator will be able to handle that. And then you can just write e to that power. And if you want to write it as a power of 10, you can use the power changing rules. So you can just say that e is equal to 10 to the 0.434. That's just because log base 10 of e is equal to 0.434. And so then we can just multiply 0.434 times 122 over kb to get it in terms of a power of 10. And so again, this is an insanely big number, and this isn't even telling us what the actual multiplicities are. This is just the ratio of the multiplicities. So in the process of melting ice, we see that we change the entropy by 122 joules per Kelvin, and that corresponds to a dramatic, unimaginably big increase in the number of microstates. And that's the lesson of these entropic processes. So we might further ask ourselves, what happens if we're dealing with a situation where the temperature isn't constant, right? When the temperature is constant, we just had delta S is Q over T. And it turns out it's not too hard to get these equations, and the book goes through the derivation, but it does require integrating. So I'm not going to make you derive them because you don't have to have taken calculus for this course. But you can imagine if you replace Q with MC delta T, our old familiar friend, and integrate, MC dt over T, then you get the delta S heat, which is basically the change in entropy that occurs when you have some substance in a constant state of matter. So for example, liquid water that you're just heating up. So if I heat liquid water from a T initial of 0 degrees Celsius, so 273 Kelvin, to a T final of, 300 Kelvin, I haven't changed the state of the water, so I don't have to use the delta S is Q over T formula. I've just heated up. So all I have to do is plug these temperatures into this logarithm and plug in the heat capacity of liquid water and how much mass I have, and I'll get delta S heat. So you can imagine if we ask you to calculate how does the entropy change when we take 0 degrees Celsius ice, melt it, and then heat it up to some temperature, we would have to add up these delta S's. We would have to first calculate delta S due to the melting, which would just be our M L F over T. And then we would have to add to that this MC ln of TF over that T of melting. And that would allow us to calculate a total change in entropy. It turns out that phase changes tend to have dramatic increases in entropy, where heating, not so much. You have to heat water quite a bit, almost to boiling point, to get an entropy that's similar to the entropy you get just from melting ice at 0 degrees Celsius. So just be aware that in general, the more entropic process will be a phase change rather than heating. And then putting this all together for an ideal gas, we have one big equation that we can use in any situation we find ourselves in to find the change in entropy for an ideal gas. So I'll try to give you some practice problems with this in the homework, and you can feel free to ask me about them. But you may have to use the ideal gas law. For example, if they tell you the initial and final pressure, you're going to have to convert that into initial and final temperatures and initial and final volumes. You see there's no P in this formula, but we can always use PV equals nRT to get the thing that we're interested in. Okay, so be aware, ideal gases, we can always use the ideal gas law in combination with any of our other tools. And so once we understand what the initial and final temperature and how many moles of gas we have for some system, then we can calculate its change in entropy very straightforwardly using this equation. Just be careful that your volumes are in cubic meters and your temperatures are in Kelvin so that you don't run into any trouble. Even though these are ratios of temperature, we do need to convert them into Kelvin because of how Kelvin and Celsius are scaled by an additive constant. It just makes things annoying. So careful with your temperatures. Always convert them into Kelvin unless they're delta T's. And so, like I said, we'll give you some practice problems for this with ideal gases. There are also some examples in the homework in section 14.3, but they're very straightforward. They're just plugging in numbers to this delta S gas formula. Okay, so moving on to section 14.4, which I'm not going to say very much about, and I'm not going to ask you many questions about. But I just want to make sure you're aware of what Gibbs free energy is. Hopefully you've seen it before in your chemistry classes and maybe have some experience with it. But it's basically this last bit of the formula here. So G is H minus TS. So the Gibbs free energy is the enthalpy, which remember was the internal energy plus the amount of work you would have to do to push the air out of the way in order for that system to, exist in the first place. So if we're creating a bunny as a magician, we have to not only give the energy to make the bunny, but also to push the air out of the way so the bunny has a place to exist within. So the Gibbs free energy is that enthalpy minus the temperature of the system times the entropy of the system. And the important thing with Gibbs free energy is that whenever we have some reaction or some process, physical, chemical process, nuclear process, the Gibbs free energy allows us to figure out if that process is something that will happen naturally or not, if it's spontaneous. And so if delta G is less than 0, then the process will be spontaneous. And like I said, this is something that chemistry classes love to go into gory detail with, because in chemistry, you're very interested if reactions will naturally happen. But what I want to highlight just quickly is that you can have processes that are endothermic, so that have a positive H. That means that they're sucking in energy from their surroundings. Typically, you would imagine those sorts of processes aren't favorable because they're taking a system to a higher energy state by sucking in energy from the surroundings. But if you have one of those systems that produces enough change in entropy, so enough increase in entropy, then it can be spontaneous. That's the beauty of the Gibbs free energy. So that's why we can have those chemical ice packs with like anhydrous urea or ammonium nitrate, where you break them open, you break open the interior and it starts to cool off and you can put it on your bruise or whatever. So those are an example of an endothermic process. So they have a positive change in enthalpy, which generally would mean they're not spontaneous. But in that process, when the chemicals are reacting and reorganizing, they actually manage to increase the entropy. And so the result is that their overall Gibbs free energy change is negative because this TS portion has a minus sign in front. So the more you increase the entropy, the more spontaneous the reaction will be. So just be aware of this. It can explain a lot of confusing situations in chemical reactions, but it also is valid for explaining physical reactions like phase changes and things. So that's why it's in the physics book. And so that's what section 14.4 focuses on. And then the next couple of sections are really more chemistry heavy. So they're doing useful work and using Gibbs free energy. These are things that I would imagine are covered in a general chemistry class. So if you're unfamiliar with them, read over them, but I don't plan on really pulling many questions from those sections or any at all for things like the final or the quizzes, although they may show up to a minor extent in the homework. So feel free to ask me about those sorts of things, but we're going to move on to the next section that I do really want to spend some time on, which is osmosis. So osmosis is something that I think a lot of times you learn about in middle school in a very vague manner and never get to dive into detail or have the tools to actually perform calculations involving osmosis. And so the book actually gives you those tools, and I really want to spend some time developing them for you as well. So we can see a couple of examples here, but before we dive into them, I just want to explain the difference between diffusion, which is what we've already learned about, and osmosis, which is what we're about to get into. So diffusion is when you have something like a pot of water that you drop a little bit of food dye into, and the food dye particles, they have some temperature, so they're going to be bouncing around. And over time, as they bounce around, they're going to spread out. So that's the random or the Trunken walk. And in that process, they're going to distribute themselves. And we know that this follows something like the square root of t. So how far they get on average is something like some constant times root t. So they're going to slowly spread out as a result of that. In contrast, osmosis requires two sort of extra things. So one extra thing that osmosis requires is a semi-permeable membrane, which allows a solvent to pass through. So the water, for example, can pass through, but not the solute. So something like a salt or a protein or something like that can't pass through the semi-permeable membrane. And in addition to that, you need some sort of concentration gradient. So on one side of the membrane, you have a lot of salt, and on the other side, you have not very much. And if you have both of those conditions, a semi-permeable membrane and a difference in concentration, then you'll get osmosis. And so diffusion is the dye spreading out, but osmosis is saying that if you have different amounts of solute, then the solvent will spread out. So it's a totally different type of phenomenon. And I really want you to spend some time trying to wrap your head around this and understand that distinction. I know it took me a while to understand personally. And so this solvent moving, it's not a result of simple diffusion. It's not just the water taking random walks and ending up on the side with more solute. It's actually something that's due to entropy. Okay, so the entropy of the system is higher when more of the solvent has moved to the side with the solute. Okay, whereas it's lower when the two are separated. So it's basically an entropy of mixing, just like if you mix chocolate syrup and milk and you stir it up and you get chocolate milk, that's a higher entropy state. There are more microstates that can describe that sort of system than the previous where you had them separate. Very, very similar for osmosis. If you allow the side that has more solvent, side that has more water, to distribute to the side with the solute, then you'll get a system with more microstates that are possible. And so as a result, you'll have more entropy. So diffusion is just a random walk. You don't need anything else to understand what's happening there. But osmosis is the maximizing of entropy. It's some system trying to come into equilibrium, where equilibrium is the state at which the entropy is maximized, or the Gibbs free energy is minimized. And so we see a couple of examples here. I'm going to start with the one on the right. This is the most simple type of system where this can occur. Basically, we have a box with two movable sides, so two pistons, one on the left and one on the right. And then in the middle of the box, this dashed line is a semi-permeable membrane that the water can flow across, but the salt cannot. And on the left, we have a solution with salt, and on the right, we just have pure water, to make it simple for ourselves. And what we find, and what the book walks you through in terms of derivation, is that there's a pressure. So the water wants to move to the side with the solution. And so if we try to prevent that from happening, we have to apply a bigger pressure here. So this is where we apply a bigger pressure, and then a lower pressure on this side. So we could call this PL, and we call this PR for left and right. So PL is going to be bigger than PR. And if we stop applying that pressure difference, then the water is just going to move to the side with the salt. And in this case, where we have pure water, it's all going to want to move to the side with the salt. And so since there's a difference in pressure, we can define this pressure gradient, PL minus PR. And this is what we call capital pi. So capital pi just has longer vertical lines and a flat top. Sorry that this PL is a little floppy here. And so this is really similar to the viscous fluid flow section, where we needed some difference in pressure if we're going to push water down a pipe, if we imagine that the water has a viscosity. So very similarly, we have a difference in pressure in this osmotic system